Good day to everyone. This is Jing Poh from Xiamen University, Malaysia. Today, I'm going to give a presentation on the topic limit point. In this presentation, I will start by introducing limit points and some definition related to limit points, stating a proof about the limit points, giving rigorous proof and some example to have a better understanding. If you like my video, please do not hesitate to like, share, and give a comment under this video. Let's move to the background of the study. Before introducing the piecewise definition of limit points, let me briefly introduce what are the limit and limit points. I believe all of you are familiar with the limit. It is a value that a function of a sequence approaches as it goes to a x value. Therefore, we can simply understand a limit point as a limit that we can achieve by using the limit of a function or a sequence. As shown in the figure on the right side, we have a sequence xn. When n goes to infinity, the sequence will approach to x. Thus, the limit of a sequence xn is x, and we say x is a limit point. In fact, a limit point is a generalization of the concept of limit. Thus, the concept of limit point is useful in calculus. It allows us to observe a function's behavior. When we have a function that is undefined somewhere, such as rational function, piecewise functions, logarithmic function, and so on, we can easily sketch a function at the point where it's undefined by using the limit of the function. That is, we can use the limit to approach the undefined part. Next, in the Euclidean space Rn, we are interested in discussing convergent sequence, open set, closed set, interior, exterior, boundary, closure, limit points, and isolated points. Now, we are focusing on limit points and the concept related to limit points. Let's start by introducing the definitions. The first and the most basic definition is the convergence of sequence in Rn. A sequence AK is said to converge to a point A in Rn if for any epsilon bigger than 0, there is a positive integer big K, so that for all small k bigger or equal to big K, the distance between AK and A is smaller than epsilon. In mathematical expression, for all epsilon bigger than 0, there exists big K in the set of positive integer. For all small k bigger or equal to big K, the norm of AK minus A is smaller than epsilon. Next, we also need the definition of open ball. Given a point x not in Rn and a positive number r, an open ball of radius r with center at x0 is defined as a subset of Rn of the form as shown in the slide. The distance between x0 and any point inside the open ball is smaller than the radius r. Moreover, we have interior, exterior, and boundary. Let S be a subset of Rn. A point x is an interior point of S if there exists a positive number r such that the open ball of radius r with center at x is contained in S. The correction of all the interior points of S is called the interior of S. On the other side, a point x is an exterior point of S if there exists a positive number r such that the open ball of radius r with center at x is contained in the complement of S. The correction of all the exterior points of S is called the exterior of S. A point x is called a boundary point of S if, for all positive number r, the open ball of radius r with center at x intersects with both S and complement of S. That is, the intersection of the open ball and S and the intersection of the open ball and the complement of S cannot be empty. Similarly, the correction of all the boundary points of S is called the boundary of S. Next, the closure of S is defined to be equal to the union of the interior of S and the boundary of S. Last but not least, we say a point x is a limit point of S if there is a sequence xk in S minus the constant sequence of x, such that the sequence converges to x. We denote the set of all limit points of S as S prime. Besides, I will also introduce a proposition and a theorem as they are useful in the proof of the theorem. We have proposition 1.1. Let AK be a sequence in Rn. Then AK converges to a point A if and only if the limit of the norm of AK minus A when k goes to infinity is equal to 0. Next, let S be a subset of Rn. We have three facts, which are the interior of S is a subset of S, the interior of S, the exterior of S, and the boundary of our S are mutually disjoint sets, and also Rn is equal to the union of the interior, exterior, and boundary of S. After introducing all the definitions, theorem, and proposition that are related to limit points, I am going to introduce a theorem with rigorous proof. Let S be a subset of Rn, and let X be a point in Rn. Then the three statements are equivalent. X is a limit point of S, X is in the closure of S minus X, and the open ball of radius R with center at X intersects X at a point other than X for every positive number R. To prove the equivalent statement, we will prove not B implies not A, B implies C, and C implies A. Firstly, not B implies not A. Assume not B, that is, X is not in the closure of S minus X. By definition of the closure, X is not in the union of the interior and the boundary of S minus X. Then, by theorem 1.2, we know the interior, the exterior, and the boundary are mutually disjoint sets and their union is equal to Rn. Thus, we can conclude that X is in the exterior of S minus X. By definition of the exterior, there exists a positive number R such that the open ball of radius R with center at X is contained in the complement of S minus X. This means for all xk in X minus X, xk is not in the open ball. By taking the complement of xk is in the open ball, we know the distance between xk and X is bigger or equal to R. Therefore, there is no sequence xk in S minus X that converges to X, which implies that X is not a limit point of S. Secondly, B implies C. We assume B, that is, X is in the closure of S minus X. Again, by the definition of the closure and the disjoint property of the interior and the boundary, X is either in the interior of X of the boundary of S. So, we prove it case by case. If X is an interior point of S, by theorem 1.2 part A, we know X is in S. Also, it is obvious that X is in the open ball of radius R with center X for all positive number R. Therefore, every open ball center at X must intersect S. On the other side, if X is a boundary point of S, by definition of boundary, we know every open ball center at X must intersect S. Lastly, we will prove C implies A. This one will be a little bit difficult. Since we assume C is true, we can choose the radius R to be 1 over k for k equals to 1, 2, 3, and so on. Thus, by C, we know the open ball of radius 1 over k with center at X intersect S, and so we can choose xk in the intersection of the open ball and S. By definition of the open ball, we know the distance between sk and X is smaller than 1 over k. Then, when we take the limit of both sides when k approaches infinity, we will get the limit of the distance is smaller or equal to 0. Since the norm cannot be negative, this shows that the limit of the distance between xk and X is equal to 0 when k goes to infinity. Here, we will use proposition 1.1, which implies sk converges to x. Therefore, x is a limit point of S. That's all of the theorem with the proof. Next, let's look at an example. We want to prove that 0, 0 is a limit point of the set S, which is equal to the set of 1 over n plus 1 for natural number n. To prove this, it suffices to prove part C of the theorem that we have proved just now. Let x0 to be the point 0, 0, and let r to be a positive number. By the Archimedes property, there exists a positive integer n0 such that 1 over n0 is smaller than r. Next, we define x1 to be a point 1 over n0, 1 over n0 plus 1. And we know x1 is not equal to x0, and x1 is in S. Also, by some calculation, we know that the distance between x1 and x0 is smaller than r. This shows that x1 is contained in the open ball of radius r with center x0. Therefore, the open ball intersects S at the point other than x0, and thus, by the theorem, 0, 0 is a limit point of S. Lastly, let's do an exercise to test your understanding about the limit points. Actually, it is quite easy and intuitive to find the set of the limit points. If you can find the set of limit points, try to prove it rigorously. That's all for me. I hope that this video can help you to understand the concept of limit point. Again, if you like my video, please do not hesitate to like, share, and give a comment under this video. Goodbye.